Welcome to the Explainer. I am so thrilled you're joining me today because we are looking at something that literally feels like science fiction, but it's happening right over our heads. We've got breaking news that is completely shaking up global aerospace dynamics. China has successfully landed a reusable rocket, securing a massive milestone in space exploration. So today we're going to take a really unique zoom-in, zoom-out journey. We'll start with the headline news, zoom all the way down into the dense, mind-bending aerospace engineering and real-time math that actually makes this possible, and then zoom right back out to look at the massive global geopolitical stakes.
Okay, let's dive into this. Here's our agenda. 1. The reusable rocket race. 2. The anatomy of re-entry. 3. The math of landing. 4. China's unique net catch. And 5. The new space race.
All right, Section 1, the reusable rocket race, a historic milestone.
For decades, rockets were just single-use. We're talking millions of dollars crashing into the ocean after just a few minutes of work. Reusability absolutely changes everything, which brings us to our immediate news hook. As reported, China's Long March 10B rocket recently lifted off, and its booster successfully pulled off a controlled descent to a floating maritime platform. This is huge. The rocket can carry a staggering payload of up to 16 metric tons to low Earth orbit. Before this, only American companies like Elon Musk's SpaceX and Jeff Bezos' Blue Origin had really demonstrated this capability. China has firmly entered the chat, directly challenging American dominance in this arena.
But to really appreciate this moment, we have to look at the history of vertical landing. The concept actually dates all the way back to 1961 with the Bell rocket belt, which was essentially a rocket pack for a single person. By the 1990s, the McDonnell Douglas Delta Clipper demonstrated a scaled vertical takeoff and landing. Then came the modern breakthroughs, right? Blue Origin's New Shepard in 2015 and SpaceX's historic drone ship landing of the Falcon 9 in 2017. And now, looking toward 2026, we have China's Long March 10B maritime catch. So this technology has literally been decades in the making, building up to today's multinational space race.
Moving on to Section 2, the anatomy of re-entry, plunging back to Earth.
Let's initiate our first zoom-in. How exactly does a massive first-stage booster return to Earth without, well, completely disintegrating? And this brilliantly illustrates the whole trajectory. Using a Falcon 9 profile as our baseline, you have the launch, followed by stage separation. The upper stage continues onto space, while the first-stage booster essentially throws itself into reverse. It executes a boost back burn, plummets through the atmosphere, deploys control surfaces, and finally performs a landing burn right before a soft touchdown on a barge. It is literally a highly choreographed mechanical ballet.
A massive part of that ballet involves grid fins. Picture this. As the booster re-enters the atmosphere, it is traveling at the speed of sound, over 1,200 kilometers per hour. To steer, it deploys these lattice-like structures made of titanium. They allow the air to flow right through them and act as absolutely critical aerodynamic control surfaces, giving the rocket precise positional control as it plummets.
But hey, before there's even enough atmosphere for those grid fins to grab onto, the rocket needs a different steering mechanism entirely. That's where cold gas thrusters come in. Mounted near the top of the booster, these systems use pressurized nitrogen to literally flip the massive rocket around in the thin upper atmosphere, orienting its engines perfectly along that return trajectory.
And of course, you need reignitable engines. The engine has to restart multiple times, first at supersonic speeds way up in the upper atmosphere, and then again at transonic speeds near the ground. But here is the trickiest part: thrust management. By the time the rocket is landing, it's burned most of its fuel. It's essentially an empty, lightweight shell. If you apply too much braking thrust, the rocket will accidentally shoot right back up into the sky. You have to perfectly balance deceleration against a rapidly changing vehicle mass.
All right, Section 3, the math of landing, computing the impossible.
Let's zoom in even further to the absolute vegetables of this explainer, the real-time mathematics. I want to pose this question directly to you. How does an onboard computer actually calculate the perfect landing for a falling object that weighs hundreds of thousands of kilograms, all while dealing with wind, changing mass, and aerodynamic drag? It can't just follow a pre-recorded path, right? It has to actively solve a highly complex physics problem every fraction of a second. Now, what's really interesting about this slide is how that math plays out visually. In the 6 degrees of freedom trajectory plot, you've got the green line showing the rocket's path, and those red and blue vectors represent the vehicle's tilt and thrust direction constantly, continuously adjusting. And then we have the time-of-flight convergence graphs. Basically, no matter how bad the initial landing guess is, the algorithm rapidly converges on the singular, perfect time and path to the ground within just a handful of iterations.
This mathematical magic trick It's called successive convexification. Finding the absolute perfect landing path while factoring in every single variable is what's known as a non-convex problem, meaning it's kind of like trying to navigate a chaotic maze blindfolded. It's just way too complex and nonlinear for a computer to solve perfectly in real time. So the onboard computer uses successive convexification to break that impossible maze down into a series of smaller, easier, convex straight lines. It is continually recalculating the fastest, safest route to the ground, minimizing errors on the fly.
But to ensure the computer doesn't generate a mathematically perfect but physically impossible flight path, the math strictly boxes the rocket into a safe physical window. We call this bounding the flight envelope. The algorithm enforces a strict glide slope cone so the rocket doesn't stray too far horizontally. It caps the maximum tilt angle and angular rate so the whole thing doesn't just flip out of control. And it manages strict thrust bounds to prevent the engine from cutting out or over-accelerating.
Which brings us to Section 4, China's unique net catch, diverging technologies. Okay, time to start zooming back out. Both the US and China are using this incredible math, but their actual hardware applications are completely diverging at the very last second of landing. Traditional reusable rockets, like the Falcon 9, use hydraulic landing legs. SpaceX has even advanced to using giant mechanical chopstick arms to catch their massive Starship booster right out of the air. But China's Long March 10B took a totally different route. They're using a maritime landing vessel equipped with a suspended wire net. The rocket has landing hooks that catch the net, and auxiliary cables immediately clamp around the booster to keep it from swinging. They completely remove the hydraulic legs. So, the crucial point is why this engineering trade-off actually matters. Space exploration is ultimately an economics game. Hydraulic landing legs are incredibly heavy. By throwing away the legs and relying on simple hooks catching a CNET, the Long March 10B strips a massive amount of weight off the rocket itself. This directly translates to an increased payload margin, and that is a massive economic advantage when your goal is to lift heavy satellites into orbit as cheaply as humanly possible.
Finally, Section 5, the new space race, beyond the atmosphere.
Completing our zoom out here, we've seen the hardware and the math, but the strategic stakes on the global chessboard are absolutely enormous. First, there's the lunar race. Both nations are targeting the moon's south pole by 2030. Why? Because permanently shadowed craters there contain ice water, which can be harvested to create rocket propellant for deep space exploration. Second, there's low Earth orbit, or LEO. Controlling LEO means deploying thousands of communication satellites cost-effectively. And finally, launch frequency. The ability to launch, land, refuel, and launch again rapidly is the absolute key to dominating orbital capacity. You simply cannot do any of this without cheap, reliable, reusable rockets.
And these two superpowers are approaching this race using fundamentally different models. The US approach relies heavily on the private sector. The government works to extract national alignment and results from private commercial leaders like SpaceX or traditional contractors like Lockheed Martin. In contrast, the Chinese approach operates under a military-civil fusion strategy, or MCF. This mandates whole-of-nation mobilization, seamlessly blending commercial aerospace innovation into state and military aerospace development. Two entirely different systems, pouring massive resources into mastering the exact same aerospace physics.
Which leaves us with this final provocative thought. As the clock ticks down to the 2030 deadline, who will secure the resources of the moon's south pole first? We've seen the 6 degrees of freedom math, the grid fins, and the diverging landing technologies from drone ships to CNETs. The engineering is mind-blowing for sure, but it's really just the tool for a much larger geopolitical race that is unfolding right above our heads. Keep your eyes on the skies, because this is only the beginning. Thank you so much for joining me on this explainer, and I will see you next time.